All right, so welcome everyone to the Schubert seminar. So today we're happy to have Kamil Rychlewicz from École Polytechnique Fédérale de Lausanne telling us about zero schemes and equivariant cohomology theory. So please take it away, Kamil.
Thank you very much for the introduction, and thank you for letting me speak here. So this is, as Leonardo noticed, this is based on results that are in a recent preprint from last month. Um, but I will start from his history. I mean, history meaning like 19th century. So so I start from Poincare-Hopf theorem. Oh, sorry. So that's what everyone knows. We take a spoof manifold X, some vector field V, with isolated zeros, and then there is this equality of the Euler characteristic of X and the sum of those indices, whatever they are, of the vector field over all the zeros. So so yeah, this is a very old result that everyone knows, but it is, if you see it for the first time, it is maybe very surprising because on the left you have something which is topological information. On the right there is something which just comes from the differential geometry and very local behavior. And on the left there is some global invariant, and this is very classical, and on the left there is just one number that represents the topology of the space. Uh, but what I want to talk about is this further extension of that theorem. It's quite a wide, quite a far extension. So this is like 100 years later. Is the theorem of Carrell and Lieberman from 70s, which says that we can actually get a lot more information about topology of X if it is an algebraic variety, a complex algebraic variety. So, well, I guess I should also add compact here. Um, so here I assume that X is a smooth projective complex variety. V is a holomorphic vector field. And again, I assume isolated zeros. There's just this additional funny assumption that the zero scheme, the zero set, is non-empty. So then let me call Z not just the zero set, but the zero scheme. So now we are in an algebraic situation. We have some vector field, and we can take not only its zero set, but also a zero scheme. Those points might be potentially thick. And what they prove is that there is some canonical filtration. on the ring of functions of Z, such that if I take the associated gradient of that filtration, oops, then I recover the equivariant cohomology, sorry, non-equivariant cohomology of X with complex coefficients. So here this statement tells me that I recover the cohomology together with the grading. So in particular, so on the left I have a grading, on the right I have a grading, but what they say is that the grading is the degree is multiplied by 2. So in particular, there is only even cohomology of X. Which somehow maybe shows why we need this assumption of non-empty zero set, because on an elliptic curve we can have an empty zero set and then we have also odd cohomology. And the thing is, there are different vector fields on algebraic varieties, and if the vector field, for example, comes from a torus action, then the zero scheme is reduced. So then the scheme structure on Z is kind of trivial. And in this situation, the whole problem of determining cohomology this way would be to find this filtration, and this is in general a very hard problem. For example, in the case of the vector field coming from a torus action. But there's an auxiliary result from 10 years later. If in addition to this vector field there is some torus action, or maybe I shouldn't, I keep some on the screen. If additionally there exists a sister action on X such that there is some non-zero integer such that when I push the vector field along that action, I get multiplied by t to the power of k. So this is an additional assumption, and then the grading f, the filtration f, actually comes from the grading defined by the torus action. So this means that if this is already defined by a grading, then the associated graded is just the same as the whole ring of functions. So in this situation, we see that the ring of functions on the zero scheme is exactly the cohomology of X. And this condition maybe sounds at first a bit exotic, but let me give you an example where this holds, and then maybe you will notice that it's actually not that rare. So an example is Pn. And then on Pn there is an SL2 action. So Pn is a projectivization of the n+1 dimensional irreducible representation of SL2. And so we have the induced action of SL2 on Pn. And in SL2, so in the Lie algebra of SL2, there is this element we usually call E, with just a single one over the diagonal. And this will give me an associated vector field coming from the action. So there is some vector field VE on Pn. And moreover, in SL2, there is already a torus. So there is this torus T minus 1. And this is in SL2. So this acts on Pn. And if I will denote this matrix by H. Oh, sorry. I will denote this matrix by HT. And then if I conjugate E with HT, then I get T square E. Which means that if I take the torus action defined by this torus within SL2, then it will satisfy this condition above with k equal to 2. So that means that well, assuming that that I can show that E has isolated zeros, then I will see the cohomology of Pn from the zero scheme of that vector field.
So,
But now if you think about it,
sorry, so Pn is the projectivization of the n plus one dimensional representation of SO2, right?
yes,
Okay,
yes.
thank you.
And now on that representation, the element E acts with well, depending on the basis you choose, but you can choose a basis such that E acts with this matrix. Maybe just once above the diagonal. And then such a matrix has only one-dimensional eigenspace. So this means that on Pn, this has only a single zero, which is the point 1, 0, 0. And now, so this lies in this affine piece. Yeah. In this affine piece of this form. And now if I look at the vector field defined by E on this affine piece, the coordinates of this vector field on this affine piece. So I will not write down how you get it, but it's an easy exercise. So you have x2, x3, x4 as the first term and so on until the second last coordinate, and then there's always minus x1 times something. And if you try to solve if you try to solve those equations, then you will see that x2 is x1 squared. Then you plug into the second one, you see that x3 is x1 cubed, and so on and so on. So this at the end tells me that or maybe I'll write it here. So x2, if I try to solve those equations, and I get x2 equals x1 squared, x3 equals x1 cubed, xn equals x1 to the n, and then the last equation will give me x1 to n plus 1 equals 0. And this way I'm able to say that the ring of functions on Z is generated by this one generator. Sorry, it's generated by this one generator x1 with one relation x1 to the n plus 1. And so there's no surprise. This is exactly the equivariant cohomology. So the cohomology of Pn. And you can see from this example that whenever I have an SL2 action, then this means I have a vector field and I have a C-star action, which satisfies the conditions we need. So then the only thing we would need to satisfy is that this vector field has isolated zeros. So this holds for Pn and for some other cases of which I will list in a second. I just wanted to let you know because this is somehow the heart of everything that will be happening later. I want to give a short sketch of the proof of this theorem.
And somehow your vector has to do with the highest weight vector of the representation. Is that? I think.
So yes, so here it's important that yeah this E, yeah, this is um, I mean, so the zero of this vector field given by E is exactly the highest weight vector.
Yeah,
Yes.
yeah.
Yeah. Yeah.
Thank you.
So I just give a quick sketch. So we have this vector field V, which is what is a vector field? A vector field is a section of the tangent bundle. And now, if I know that it has isolated zeros, this means that the zero scheme is of the codimension equal to the dimension of the whole space, which also happens to be the rank of the tangent bundle. And if this is the case, so if the zero scheme is of the codimension equal to the rank of the bundle, then there is a causal resolution of this zero scheme. So how does this look like? So I have the structure sheaf on the whole X, um, the cotangent bundle, so dual of Tx. And here there's the contraction with the vector field. There is a contraction from two forms and so on. And so then this is a resolution of the zero scheme of the structure sheaf of Z. And what it means is that if I try to compute the ring of functions, or more generally cohomology of Z, but in this case the higher cohomology will be trivial because Z is of dimension 0, then I can equivalently take the hypercohomology of this resolution. So H star Z of Z is the hypercohomology of this sequence, of this complex. And then I can write a spectral sequence where in the first page I will have cohomologies of the sheaves that show up in this complex, and this will converge to what I'm trying to compute, so to the cohomology of Z. Now there is some argument. So then now there are two ways to go. So one way is the original argument of Carrell and Lieberman. They use hard Lefschetz to show that the sequence degenerates on E1. A different argument now is that, I know that in the case that there's additional work. If my conditions are satisfied together with this auxiliary action of C star, then that C star has isolated torus fixed points, and in that case my cohomology is state. So another argument. Isolated torus fixed points. And that means that HQ x omega x minus p is non-zero only if q plus p. Okay, that's written in a funny way, but this means that we only have HP of omega p cohomology. And so this means that actually we only have terms on the diagonal, so the differentials have to be zero. So in any case, the spectral sequence degenerates on the first page. And this means that H0 of Z is the direct sum of those HP x omega p. And this is exactly the cohomology of X. And then additionally, there's some work to show that we can lift the C-star action to the Kosovo complex. And so this way we recover the grading on cohomology. Okay, so that was the kind of historical sketch, what we knew already 50 years ago. But this result brings a lot of questions. So let me pose the questions here. So first of all, what happens if you don't have this auxiliary C-star action and then the filtration might potentially be non-trivial. So I will call this zero because I will not address this question later. But I'm just noting this here, and because I want to say that this is in general very difficult, as I mentioned before, for torus, just a vector field coming from a torus action. There's no real information in the zero scheme, so there must be something very non-trivial in this filtration. I mean, the only work I know along those lines is this paper by Kumar Skave from 2005. Where he computes this for toric varieties. And there we know anyway what the cohomology is, but finding that filtration is very non-trivial and is connected to some combinatorics of the polytope. So it's already quite interesting, but this is I'm gonna move to the second page, another page, and state the problems which I want to address later in this talk. So I will assume from now on that we always have either SL2 acting, or actually, if you follow it closely, it's just enough that the Borel of SL2 is acting on X for the assumptions to hold. And then question one is what happens if the zeros of E are not isolated? So there's this vector field defined by my element E in the Lie algebra. There is this C-star action that's nicely compatible with it. But of course, in many situations in life, when I have an action of a group, I have a vector field that might not have just isolated zeros. And then the second question is, can we say something if X is actually singular? So then this is also a question what we consider vector fields on X. And another question is what we like to do is not just usual singular cohomology, but equivariant cohomology. So let's assume that I have some group G acting on X. It might be just the SL2 with which I started, or maybe something bigger. And then the question is, can I somehow recover the equivariant cohomology of X using similar methods? So I also will maybe mention first what we already knew some time ago. So the singularities were already considered by Carrell and his collaborators when trying to tackle cohomology of Schubert varieties. So that was most important result was Achilles, Carrell, Lieberman, 86. So that was Schubert varieties. So this way they were so they were able to see the spectrum of cohomology of the Schubert variety, even a singular one. And then surprisingly, what they considered to find those homology rings was what they called the deformed zero scheme, the deformed deformed zero scheme, and this led in 2004 Brion and Carrell to show that actually this deformed zero scheme recovers C-star equivariant cohomology. So I'm not writing very concrete statements for now because I will in a second put it all together in one framework. And before and so this will all be in the world of equivariant cohomology theories. So for that I need a little bit of theory, and I see that I'm 29 minutes in, so maybe this is a very good moment to take a break.
Yeah, yeah. So let's take a break. Yeah, let's take maybe a 5 minutes break. So 5:04.
Mhm.